All right. Hi, everybody. It is 9 o'clock and let's begin. So you can see I've written an announcement at the top. This is so my advisor has begun this committee for diversity in the mathematics department, and she's holding these perspectives for prospective majors and minors meetings. And the goal is to try to get more students involved in the math department at Rice, more undergrads to choose math as a major or a minor. The idea is that most people who do math at Rice have already decided that they want to do math prior to coming to Rice. So um, there's a virtual mathematics meeting on Zoom, and I'll post the information on a Canvas announcement. But basically, you get to go there and just kind of talk to professors about what it's like choosing math as a major or a minor, and it can be a really helpful experience. So I thought I'd pass along that to you. I think everybody in this class could, at the very least, get a math minor. I don't have doubts in any of you. Okay. And so I'll post some more information about that on Canvas. Now, I thought I'd try a new feature with the Zoom today. So you can see I've got a warm-up going on. In a second, I'm going to open up a poll. So you should be able to, I'm going to launch a poll and you'll be able to answer. So in the question I've written below, we have a vector field V, which is, I'll draw it in green. The vector field is the upwards everywhere vector field. So that's the green vector field. And there I've got a vertical blue cylinder S with an outward normal vector field N. So I'm going to launch a poll, and I'm going to ask, what do you suspect the sign of the flux integral V dot N dA? What do you expect is the flux integral positive, negative, or 0? Do you suspect? Okay, we've got 4 people so far. Okay, cool. This is great. Almost everybody's voted so far. Okay, and all right, perfect. Yeah. All right, most people are getting the right answer. This is excellent. Okay. Everybody's voted, so I'll end the poll. And good, the answer is 0. So the flux is equal to 0. And that's great because you can see, I'm going to zoom in for a second, the green vector always forms an orthogonal pairing or a right angle with the red. And so you're adding up 0 everywhere, so the flux should be 0. Great, I love it. Okay, I can share results. Awesome. I'm going to close this, and I've got the chat open. All right. So I'm going to move into the topic of the day. And so the topic of today, what we'll be studying is this is Stokes' theorem in higher dimensions. And this is one of the most important theorems. Okay, so Austin's asked a question to the chat. I don't know. Okay, so sorry, Austin, you'll have to figure that out. I don't know how to help that issue. But this theorem is one of the fundamental theorems of calculus, and it's going to use absolutely everything we've done so far in class. We're going to use integration, partial derivatives, parameterizations, vector calculus, the works. So this is sort of a crowning moment in the class. And I think what I'll actually do right now is I'll just state what it says, but we're going to spend a good chunk of the class actually picking it apart and actually figuring out what it is. So the theorem is that basically, if you take a flux integral of the curl of a vector field, and you dot it with the outward normal, we'll talk about all of this in a second, and you integrate that over some surface, this should essentially be equal to the work integral done along the boundary of the surface. So we're going to unpack all of this, but this is what we're working towards. And it should look a lot like the more simple version of the Stokes theorem that you've seen so far, except this was a region and curl was a scalar number, not a vector. So let us unpack this for a second and let's get an intuition for what curl as a vector really is. Now I've actually put a line over the top because remember that if V is a vector in 3D, then curl is a vector. So I want to remind you, if V of x, y is a two-dimensional vector field, then curl of V is a scalar. That's just a number. And remember, it's telling you it's a number at a point. So if I'm in the xy plane and I drop a little pinwheel at a point, so that's my little pinwheel, my little windmill, what the curl tells me of V at that point P, it's telling me how much clockwise or counterclockwise rotation the pinwheel would experience. So this is curl in 2D. But now let's work with in 3D. So what is curl of V when V of x, y, z is a three-dimensional vector field? Okay, so this is the question we're going to answer. And I want you to know that in 3 dimensions, rotation always occurs around an axis. So in 3D, all rotations occur along an axis. Basically, take a basketball in your hands and like spin it in some way. No matter which way you spin it, you're always going to have 2 fixed points. There's always an axis of rotation. Even if you do a couple different rotations composed with each other, like an east-west rotation and a north-south. If you do this, you can actually believe that if you really look at it, no matter how you rotate a basketball, 2 of those little dots will always be still, even if it's a north-south composed with an east-west. So all rotations occur along an axis, and I can actually tell you what happens. So in fact, curl of V is some vector field with 3 components, and the direction of this vector describes the axis of rotation. Okay, and the magnitude of the vector describes how fast you would feel like you were spinning. So it describes the size of rotation, describes how much rotation occurs. How much counterclockwise rotation occurs along that axis. How much counterclockwise rotation occurs throughout the axis. Okay, so that's what curl is telling you, because rotation is more complex in 3 dimensions. That's why curl is a more complex object when the vector field has 3 components. So let's kind of I'm going to move the page for a second. I bet some people are still writing, so I'll hold here. But on the next page, I'll kind of explain what this pinwheel story looks like in 3D. Okay, so I'm going to draw a picture. So actually, let's say, so to compute how much a propeller will spin, or a windmill, or what was I saying? I was saying a pinwheel will spin in the presence of a vector field. We take the dot product. of, okay, I'll draw the picture so far. So in 3D, there are a lot of different ways you could orient a pinwheel. So here's a little point in 3D space. It's in X, Y, Z space, and the gears of the pinwheel, the arms of the pinwheel sort of are going to form some like little disc right here. Okay, so they kind of have some, they can catch wind as they spin, and the axis they're around is something, I'll call it like this. So that's going to be the axis. Okay, so you're wondering, there's some vector field that's happening out here. I won't draw too many vectors, but you can think of it as wind, and you want to know, if I place my pinwheel right here, is it going to spin at all? Is it going to spin clockwise or counterclockwise about that N? And to actually compute what happens, you'll compute this. So at the point P, you have two vectors. You have N, which is the normal vector coming out of your propeller. It's describing how you've oriented the propeller, which has nothing to do with the vector field. That's the choice you've made. But also at that point P, you have a second vector. So I'll draw it up here. So that vector is going to be curl of V at point P. So you've got two vectors based at that point. And so if you want to know how much spin you'll have in this green pinwheel, you'll take the dot product of N and the curl. Now this is an honest to God number, and this tells you how much counterclockwise rotation the pinwheel will exhibit. That's a number. Like after you've placed your pinwheel in 3D, this number will tell you how much you're spinning. And so let's look at the situation that I've drawn. In this situation, I've kind of drawn my N and my red vector and my purple vector so that they're making an acute angle. It's smaller than 90 degrees. So in this case, you anticipate that the dot product will be positive. So in my drawing, N dot curl of V at P is positive. Thus, the pinwheel probably will spin counterclockwise about my normal axis N. Okay. If I had sort of twisted it the other way, you'd expect counterclockwise rotation. That's kind of how you'd. If I had drawn it upside down, the angle would be obtuse. Okay. Okay, so that's the motivation of what 3D curl is. So let's do a quick little example. Okay, I'm going to do an example on the next page. There's lots of writing and I'm switching pages a lot, but if anybody needs me to go back, just say it in the chat. So let's do an example. I'm going to let V of X, Y, Z be equal to YZ, comma, I think that's negative XZ, comma, XY. Okay, so yeah, I'm going back for a second. So in this next example, what I'm going to do is I've written the example of the vector field. It's like some really crazy twisty windstorm. We don't know exactly what it is. I can't plot it. Actually, I went online and I was able to find a pretty good 3D vector plotter, and there's some pretty good ones. I think one from GeoGebra is nice. So look for GeoGebra to plot stuff. But anyway, this is some crazy windstorm and the vector's all over the place, and we want to know how much a pinwheel would spin if we plotted it at different spots. So if you wanted to, so I'll say, what is the circulation about the vector, about the unit vector n, which is 1 over root 3, 1, 1, 1, at the points A and B, where A is equal to 1, 0, 0, and B is equal to 0, 0, 1. So what you would need to do in this situation is step 1, calculate the curl of V. And I've done this for us because we know the curl is a cross product and lots of crazy partial derivatives, and it takes quite a bit of time. But I computed that the curl of V was 2x comma 0 comma negative 2z. So you can just take it for my word that that's what the curl turns out to be. I trust all of you could compute this. And then the step 2, evaluate this vector curl of V at points A and B. So curl of V at point A is, I got to plug in 1, 0, 0, and I get 2, 0, 0. And curl of V at point B is equal to 0, 0, 1. Ah, that's wrong. That's not right. 0, 0, negative 2. Okay, and so thus we have everything we need, because all we need to do is take a dot product with n, and then these two vectors. So I can write the answer. I can say, thus, at A, the circulation, or the rotation about n is, okay, I've got to do n dot 2, 0, 0, and this gives me, you trust me, that turns out to be positive 2 over root 3. Okay, and then at B, you can see I'll just have n dot 0, 0, negative 2, and that is negative 2 over root 3. So I'll draw a picture. I'm not going to move the page yet. I'll just lasso everything. I'll make it small to fit a picture. Okay, so in 3D, what this tells us is I've got x, y, and z. I can plot my points, A and B. So A is out here. This was A. And B was up here. And my n was the vector, is a unit vector that points like in the 1, 1, 1 direction. So that's out here. That's out here. And these make I have little pinwheels attached to the base of the normal vectors. And what we found? We found at A, we got the number was positive. So this was A. So I'm going to experience counterclockwise rotation. So, okay, hang on. It's kind of like this. So counterclockwise rotation is going to look like this. So my pinwheel would spin that way. And then over here, I have something kind of different. I have a negative number, which means I have clockwise rotation. So the picture isn't great, but that means it's going to spin this way about that axis. So that's kind of how you can utilize curl to tell you geometric information about how, basically how much your vector field is twisting and in what direction in 3D. So that's kind of a dot product will achieve that for you. And if you want to know why, I think there's there's a geometric proof, I believe, in the OpenStax, but because we've had an abbreviated semester, I just don't really have the time to explain to you why this fact is true, why taking a dot product with curl actually computes the rotation. Okay, so I'm going to actually start talking about flux integrals and how this fits into flux integrals. So I'm going to kind of explain what happens in Stokes' theorem. Okay, I'm going to flip the page. All right, let me know if I need to go back. All right, so now we're on page 5. And all right, here's the setup. So we're going to have S is an oriented surface in 3D space. So I'm sure all of us have had practice with this. I mean, you could think of S as a cone, a sphere, a cylinder, a parallelogram, just a 2D object sitting in 3D. So it has area, but not volume. It has area, but not length, Okay. It's an oriented surface in 3D space with a chosen unit normal vector n. Okay, so I'll draw a picture in a second, and I'm going to say let C be its one-dimensional boundary. Whose orientation agrees with the orientation of S. Okay, so let me explain what all of that means. I'll draw my picture. I'll draw S as my nice surface. It's looks like a wavy flag, all right? Over my surface, I have a unit normal vector field, so I'm gonna just say this is n. So in red is n, okay? And then on my boundary, I have a curve C. And somehow I have to realize, am I going clockwise or am I going counterclockwise? Kind of like should this curve C, should I be going this way or should I be going this way so that the orientation agrees? So the idea is that the orientation of C agrees with the orientation of the blue S when, as you walk along the green path and your head is standing up, like imagine you are a red vector and you are walking along this curve, then your left arm should be inwards, should be on the inside of the surface. So as you walk along C, that means this way is the positive orientation. So we'll have much more practice with this later. If that doesn't make sense to you right now, it's just a convention that mathematicians have used, that the left-hand side is how this works. Anyway, if that bothers you right now, we'll talk about it later. So, and the third thing we have is we have a presence of a vector field, an ambient vector field. It's kind of doing some stuff. So this is V. All right. So what I want to do is I want to look at the following flux integral. So I want to look at the double integral over my surface S. And what am I going to accumulate over the surface? I'm going to dot something with n. I'm not going to dot v. That's what we were doing yesterday. We were dotting v, and that was the flux. We were determining how much vector field was moving through the surface. Instead of dotting with v, I'm going to dot it with the curl of v. Okay, that's kind of tiny. But remember, I'm taking a vector, and I'm dotting it with my normal. So last time when we did a flux integral, this is on the side, remember we did something like, I'm not going to call it v, we did say w dotted with n over the surface dA. This was our flux integral. And, we actually had practice with this morning. Everyone has intuitive understanding of what this thing is. This is telling you how much w is flowing through the surface n. So you're right to think this number is telling you how much curl of V flows through the surface S. You're not wrong to think of it as that way, because that's how, it always works when you're dotting n with some vector field. But I'm going to say this isn't the most intuitive understanding of this integral. So this isn't wrong, but I'm going to say not so intuitive. Let's think about what this is accumulating at every single point on the surface. So really, at every single point on the surface, we're accumulating the quantity curl of V dot n. And we know what this number is. This number describes the amount of rotation that V is exhibiting around N. So remember, this is rotation at a point that and this is counterclockwise rotation at a point that V exhibits around N. So it's the same thing as saying the counterclockwise rotation of V restricted to the surface S at that point. So restricted to surface S at that point. So what we're doing is we're going over the surface, we're seeing how much rotation falls on the surface at that point, and we're taking the aggregate, we're summing, we're integrating over the full thing. So thus you can interpret this quantity as the total accumulation of V's rotation on the surface S. Okay, so I know it technically is a flux integral. When you have to set these things up and compute these things, you'll set it up just like a flux integral like we did on Monday, where we took a dot product, we took the U cross V, we dotted it, we integrated out the U and the V variables. That is how mechanically you will compute this number right here that I'm highlighting. But how you should intuitively understand it is this is the rotation. This is how much like swirling the vector field does on the surface. And so I'm going to flip the page for a second. And so this really tells you that, if I have this surface, this is my big surface S, and I have a little bit of a pinwheel at every single point. There's my little pinwheels all over the surface, and they each have their little outward normal vector. I'm really racking up, here I might have counterclockwise swirl, but here might have clockwise swirl. Maybe there's counterclockwise, and you start putting these pinwheels next to each other, and if I have counterclockwise and then clockwise, I might cancel out. It's a full zero rotation in there. And then over here, this one looks like counterclockwise rotation. I start sort of combining these three pinwheels. Well, maybe now on the whole, maybe it's a little bit of clockwise rotation. I start increasing more and more and more up until the boundary. And that's why the total accumulation of curl on the inside can be measured by how much work is done on the outside. So the total rotation on inside, sort of all the cancellation that might happen on the inside, is going to equal to the rotation done on the outside, or force exhibited on the outside, which by outside, I mean boundary. And this thing right here, as we said, is the double integral of the flux integral dot n dA. And this is the work integral along the boundary, V dot T ds. And this is Stokes' theorem in higher dimensions. So it looks really similar to what we had before. I just want to remind you that before we had the double integral of curl of V dA over a solid region in the 2 plane was equal to the same thing on the right, V dot T dA. So if you had intuition there, this is the same reasons are applying here, but now instead of doing like a 2D region in the plane like this was kind of your R. Now you're allowing your region to be a flippy floppy surface in 3D, like up here. And so the same principle applies. It's the same. If you understood why this was happening, this is the same principle that's going on. Okay, so this is Stokes theorem in higher dimensions. And so I'll say it's important, you need that the orientation of C agrees with the orientation of S. That's a little caveat that you need right there. Otherwise, you'll have to correct it with a negative sign. Okay, and wait, this was page 6. Okay. So we haven't done any computations or calculations today. So let's actually, well, I guess we did that little curl example where we took the dot product, but that was pretty low key. Let us do an actual solid example. Let's just see how this all works out. Let's do an example where we're going to compute this left-hand side. So I'll highlight that in yellow. We're gonna do an example, we'll compute the yellow, we'll compute the blue, and we'll see that they're the same number, and that's not an accident. It's the reason that they're the same is because of this picture up here. Okay, so let's move on. Here's page 7. Let's do an example. And we're going to let v of x, y, z be equal to negative y, comma x, comma 0. Okay, so I can draw that for y'all. Remember, this is that tornado-looking vector field. We've done this many times. So this is x, y, z, and I'll do it in purple. So they have no z component. So it's just the rotational vector field in the xy plane, but then multiple sheets lifted on top of each other. So it kind of looks like a sort of like this thing. Okay, sort of it's like spinning like this. Okay, so that's my v. And then let's think, I want to be doing a surface integral. So I'm going to say, let S be the unit hemisphere centered at the origin above the z equals 0 plane. And then what else? I need to tell you the outward normal. So then the n is the outward normal. Okay, so I'll draw that on top of my picture here. It's gonna get a little messy. In fact, I'm going to zoom in on that so you can see my picture. We have a unit hemisphere. It's the top of this thing right here. That's my S, and the normal vector field comes outwards like this. Remember, there are two choices. I could have gone out or I could have gone in, but I'm choosing that the outward is determining the positive orientation. Okay, so that's S and N. And finally, I'm going to tell you what the curve C is. So, and then C is the equator in XY plane, the unit equator, oriented counterclockwise. So I'll do that in green up here to kind of match the chromatics of the previous set of notes. So coming up here, that is the equator down here, and I'm moving counterclockwise. Okay, and you can see that, in fact, in this case, C is the boundary, or the edge, of S, and the orientations agree, because as you walk along the curve and you're like a vector, your body is a vector, your left hand will be on the inside, will be on the side of S. That's what I've described to you as the how to find a positive orientation. Okay, so we have everything to set up Stokes theorem. So the first thing we want to do, so one, I'm going to say compute the flux, so curl of v dot n dA over S. The second thing we're going to do is going to compute the single work integral over C ds. And the third thing we'll do is compare. And we better get the same things. Compare values for 1 and 2. Okay, so for step 1, this is going to be the longer step because we've got to do curl and we have to do a flux integral. And we know that that takes a lot of work, but I've done lots of this on my own time, so I can show you the steps involved for 1. I computed that the curl of v is equal to 0, 0, 2. Okay, you don't need to do that. You can just take my word for that. I've come up with a parameterization. So I've parameterized of S turns out to be R of UV is equal to, remember, spheres are awful. It's just like trig galore. So I've got cosine of U, sine of V, comma, sine U, sine V, comma, cosine of V. Okay, and I'm going to let my U range between 0 and 2 pi, and my V is going to range from 0 to pi halves. That's going to give me that upper unit hemisphere. And then my partial U turns out to be, I'm gonna stop writing cosine and sine and drop the OS and the IN. So it's cosine of U, cosine of V, comma, sine of U. This is, let me erase. This is my partial V. Partial V is this thing. Sine of U, cosine of V, comma, negative sine of V. Partial U is the following. It's negative sine of U. I probably don't even need to, negative sine of V, comma, cosine of U, sine of V, comma, 0, and my partial V cross my partial U turns out to be this thing. It is cosine of U, sine squared of V. Aren't you glad that we didn't do this together? This is, sometimes it's nice when someone just shows the answer. Okay, cosine of V times sine of V. Okay, so what I'm going to do is minimize all the stuff again so I can stay on this page. Resize, okay. All right, so we have essentially everything we need to compute the flux integral. So we can do 1 now. So 1 now says the curl of V dot N dA over S is going to equal the integral from 0 to 2 pi, the integral from 0 to pi halves. Okay, I've got to take my vector field. So this is, my curl is 0, 0, 2. I've got to dot it with this thing, this huge puppy right here. And I could write the whole thing all out, but realize that after I take a dot product, the first 2 components don't even matter. So I'm going to write something, comma, something, but the z component certainly matters. So that's cosine of v, sine of v. I'm going to do that dot product, and then I'm going to be doing dv, du. And so I'll be getting the double integral, 0 to 2 pi, 0 to pi halves of 2 cosine of v sine of v. Okay, wait. Okay, I'm looking at my work and I'm getting something interesting. Okay, so okay, let's just keep going. I'm predicting something bad is going to happen. So this is dv du, okay, and then this should be 4 pi times the integral from 0 to pi halves cosine v sine v dv 4 pi times sine squared of v evaluated at pi, halves, and 0. So I did a really quick u substitution. Okay, sorry, I'm kind of panicking right now because I'm wondering if something bad's going to happen. Oh yeah. They're not. These aren't 0. I should say this is stuff, and this is stuff because it doesn't matter if I take that dot product. And I didn't want to muddy the page with any extra things. So I'm getting 4 pi, but I think the other thing is 2 pi. Okay, so I believe right now that this whole answer is 4 pi. Okay, so that was answer to 1. Let us on the next page do 2. And let's see what we get. Wait, I'm just looking at this thing, and then I know. I'm really sorry. Okay. Let me just this is page 8. So let's do the integral of c v dot t ds. So to parameterize the c, I can do r of t is a cosine of t, sine of t, comma 0. The reason why I got the 0 going on is because I'm in the z equals 0 plane right there. That's z equals 0. And I know I'm doing a counterclockwise circle, so that's telling me the cosine comma sine. Okay, so this tells me if I know v is negative y comma x comma 0, then that means if I sub in my values, I'll get v is negative sine of t comma cosine of t comma 0. And I can also tell you what my r prime of t is. This is negative sine of t. It's the same thing. Cosine of t comma 0. And then this thing is going to be, so the integral of v dot t ds is the integral from 0 to 2 pi of, well, if I take that dot product, I'll write it out. That's sine of t cosine of t 0 dot negative sine of t cosine of t 0 dt. You can see what'll happen. This is going to give me a sine squared of t plus cosine squared of t dt. That's the integral from 0 to 2 pi, which is 1 dt, and that's 2 pi. So, all right. Pretty sure. Oh, thank you, Daniel. Thank you, Daniel. Okay. I was really panicking just now. Okay, so I did this computation really fast right now. So, because I wanted to make sure I got 2 pi, and we did. So, okay. So I went fast. Sorry, everybody. I'm going to go to the previous page. So we got 2 pi here. And the previous page, supposedly I got 4 pi. And that's bad because I should have gotten the same number for 1 and 2. And Daniel corrected me. Thank you very much. You're right. This should be, after I integrate, this should be sine squared over 2. And that kills the 2 and the 4 pi. So this was wrong. So this should be 4 pi over 2, which is 2 pi. Thank you. Okay. You couldn't see me, but I was sweating actually quite a bit just now. So these numbers are both 2 pi. That's the price you pay for doing stuff too quickly and not showing all of your work, right? So both of these numbers are 2 pi, and so that's good. This is not by accident. So both of those numbers are 2 pi, and that's by the higher dimensional Stokes theorem, we get 2 pi and 2 pi. And you can see this computation was much uglier, took much more work. Over here, I kind of just whipped this out in a heartbeat. So this was computation of number 2. We got 2 pi for both of them, so good. Okay, so let's do another fun one. I think we have 6 minutes left, so let's do the following. So let's do another example. I'm going to say compute the following work integral. So it's a v dot t ds, and it's the following. So v is equal to z comma x comma y, and c is the triangle in 3D. So I say the edges, it's a one-dimensional thing, is the I guess I'll fix this, is the boundary of a triangle, is the edges of a triangle in 3D with vertices A, which is 1, 0, 0, B, which is 0, 1, 0, and C, which is 0, 0, 1, and then traversed in that order. Remember, I need to tell you an orientation. So that's what I mean by traversed in that order. So let me make this small. Okay. And this means if I draw a little picture, here's my X, Y, Z. It means here's point A, here's point B, here's point C, and I'm going from A to B, from B to C, and C to A. Okay, so if we really wanted to compute this integral, we see we have 3 line segments, so we would, in theory, need to do three separate parameterizations. So that's kind of a headache. So here's the trick, not the trick, but instead of using 3 parameterized segments, I'm going to say use Stokes theorem. So Stokes theorem says I'm going to bound this triangle by a surface, and I'm not even going to call it S, I'm going to call it T for triangle. So bear with me while I zoom in up here. As I zoom in up here, I see that I have this sort of triangle in here. It's really a face of a plane. So I'm going to call that T. And I have 2 possible options for a unit normal. I could use n1 or I could use n2 as a unit normal vector. Now let me ask, you can write this in the chat, I haven't made a poll. Which normal vector would I pick so that the orientation of t would agree with orientation of the curve C? Should I pick n1 or should I pick n2? Which way is going to have agreements? As I walk along n1, yes, good. Okay, 3 people for n1. Excellent, excellent, good. n1 is what I want to pick. So I'm almost out of time. I have 3 minutes left, but I think I'll have enough time. So the Stokes theorem says that this integral v dot t ds actually will equal a double integral over my triangle of the curl of v dot n1 dA. And I can tell you right now how this stuff works out. So the curl of v actually works out to be constant. I wrote it down. So curl of v equals 1, 1, 1. It's constant, which is super nice. Then I can also tell you that n1, it's to get the unit normal vector, it's actually also 1, 1, 1 over root 3 to make it unit. And this is because t is on the plane given by x plus y plus z equals 1. And remember from months and months ago that you can peel off a normal vector just by looking at the components of that. So finally, I can actually tell you what this thing is. This is the double integral over t, 1, 1, 1, dotted with 1 over root 3, 1, 1, 1, dA. But lo and behold, if I do that dot product, that becomes, I think, 3 over root 3 dA. And I can pull that out. That's 3 over root 3 double integral t1 dA. And this is the area of the triangle. So this is 3 over root 3 area of the triangle. And you can actually figure out what that is using like SOHCAHTOA, triangle rules, all sorts of stuff, 1/2 base times height stuff. So in fact, you can do this sophisticated work integral without ever having to use integral calculus, just by using this, this is a cute little trick that happens. I think the actual area is, I said root 3 over 2, so this is, you can check this if you'd like. This is 3 over root 3, root 3 over 2, so the final answer is 3 over 2. And so if you really wanted to check your work, you could go ahead and parameterize the 3 edges of this triangle, do the work integral, see what you get, and at the end of the day, if you add up all 3 of them, you better get 3 over 2. And that is 950, and that's all we can cover right now. So I will stop recording, and if people have questions, they can ask them. Okay, let's do
Leo,
this.
could you explain the orientation
Yes.
again? Just like how